Alright, okay, so this video is part 2 of this lesson. So again, I'm just recording this for those that were absent, need a little bit help with this problem. Okay, so let's try to look at the important information. So Kelsey is kayaking on a river. Okay, so she travels 5 miles upstream and 5 miles downstream in a total of 6 hours. Okay. In still water, Kelsey can travel at an average speed of 3 miles per hour. And we need to set up a rational equation to determine the average speed of the river's current. Okay, so let's try to analyze some of the information. Okay, so just like the other problem, answer will be the average speed. Oh yeah, I forgot to underline that. So to determine, we're trying to determine the average speed of the river's current. Okay, so that is our answer. We're trying to determine the average speed of the river's current. Okay, Kelsey, we need to figure out how many hours she spends kayaking. If you look at the problem, she spends 6 hours. 6 hours kayaking. Now, how many miles upstream and downstream? She travels 5 miles upstream and 5 miles downstream. Her average speed in still water, right, is going to be 3 miles per hour. I'm just going to write it in the same format as the one below. mph, miles per hour, that's fine. That works. Okay. Formulate a plan. So now let C represent the speed of the current in miles per hour. All right. So let's just draw a picture. So let's say this is the river. Forgive my wonderful drawing skills. So this is a river. This is a boat. Kelsey is on the boat. And we know the current. So if we think about water, right? So current will go usually, well, one direction. So the current might go this way. That's C, right? So think of it as like those of you that I guess go sandies or like to boogie board or something. Usually the waves go in one direction, or like, and that's how you essentially catch the wave. Okay, so anyway, so when Kelsey is going upstream, so think about it. So Kelsey wants to go this way at 3 miles per hour, right? If this represents upstream, her rate is going to be her speed in still water. So that would be her speed here. But if she's going upstream, we have to subtract it from how much how much the current is pulling her back this way. So this is going to be her speed in still water minus C. Now, let's say Kelsey is going downstream instead. So if I were to draw this the other way, right? Let's say she's at Sandy's catching the wave, bodyboarding, whatever she's doing. So she's going this way, trying to catch the wave, or going, yeah, in the river. But anyway, so she's going this way instead. She's going downstream. She's going with the current. So since she's going with the current, her speed is going to be how much she can travel by, which is going to be 3 miles per hour. But instead we're adding the current. So if we're adding, this is going to be her speed in still water plus C. Okay. The variable C is restricted such that the speed of the current is going to be greater than, oh, there's an error. This is a typo. Oh shoot, I just printed this out too. speed of the current is greater than 0 miles per hour. Okay. Yeah, I need to tell you guys that in class. It's okay. Miles per hour. Okay. So, complete the table. Okay, so we're gonna use this formula. So some of you might be familiar with it. If you guys, I think it's 9th grade physics, you should have learned something like this, or maybe even before that. But we're using the formula distance equals rate times time. Okay, so let's go ahead and fill out some of the information. So let's look at this. So we want to represent her distance going upstream. Going upstream, she travels 5 miles. So we're going to write that here. So she travels 5 miles upstream. She also travels 5 miles downstream. That goes here. So 5 miles downstream. Now, it says that Kelsey will spend 6 hours kayaking. So we know the total time here that she spends is going to be 6 hours. Okay? So we know that she's going to spend 6 hours here. Okay, now let's look at our rates. So our rates are described with this step. So her rate is equal to her speed. So her speed in still water is 3 miles per hour. So going upstream is going to be speed in still water, which is 3, minus the current. Now, if she's going downstream, she's going with the current. So this is going to be 3 plus c. Okay. Now what we need to do is we can manipulate this formula. So D equals rate times time. Now essentially, if you want to write a formula for time, we can divide both sides by r. We cancel this out. We have time equals distance divided by rate. So if we're to express this, time is going to be 5 divided by 3 minus c. And we know going downstream, it's going to be 5 divided by 3 plus c. Okay? And the total amount of time that she takes is going to be 6 hours. Okay? So if I were to write that, so this is 5 divided by 3 minus c plus 5 divided by 3 plus c equals 6 hours. She takes a total time of 6 hours. Okay? And that is essentially it. That's how you set up the problem. Okay. Okay, so the next one. So let's look at this. Riverboat travels at an average of 14 kilometers per hour in still water. Okay, riverboat. So I can underline some important information I see. 14 kilometers per hour in still water. Riverboat travels 110 kilometers upstream and 110 kilometers downstream in 17.5 hours. So we need to set up a rational equation that determines the speed of the current of the river. So we can set it up kind of similarly. So I'm just gonna create my little box thing, right? We have distance equals rate times time. Distance equals rate times time. Oh, I think we only need 2 boxes for this actually. 2 boxes. Okay. Alright, so if I were to do this, so we know we just follow this format. So upstream, so one is going to represent upstream, the other one is going to represent downstream. Okay, so upstream, she travels 110 kilometers up. So this is 110. Oh, I should write my units so you guys know what the units are. The units, this is going to be kilometers. This rate is going to be actually, well, that's what we're wait. Yeah, so this rate is going to be kilometers per hour. And this time is going to be hours. Now if you wanted to, yeah, so this is kilometers, and this time is going to be hours. So rate is just distance divided by rate. So that's how you get that. Okay, well, anyway, we said that this is 110 kilometers and 110 kilometers down the same river. Okay, total amount of time is going to be 17.5 hours. Okay, now the riverboat, it travels at 14 kilometers per hour. So whatever this boat is, right? The boat, we know it travels for sure 14 kilometers per hour. Okay, so if you're going upstream, this is my current, you're gonna go against the current, right? So this is gonna be 14 minus C. You're fighting the current to try get higher. Then if you're going downstream, you're gonna go with the current. This is gonna be 14 plus C. Okay, now in order to find time, we do just like what we did here. It's going to be distance divided by the rate. So 110 divided by 14 minus C. This is 110 divided by 14 plus C. So this is just distance divided by rate. And that's how I get time. Now, if I were to set up an equation, now this is just going to be time upstream plus time downstream is going to be the total time, equals total time. 110 over 14 minus C plus 110 divided by 14 plus C equals 17.5. And that is what essentially what we'd have to do in order to solve for the current, if we had to do that. Okay. Now, one more problem. Okay, last one. Airplane travels at an average speed. Okay, so average speed of 534 miles per hour, no wind. So that's like the still water thing. Airplane travels 1,200 miles against the wind, 12 miles with the wind, in a total of 4.5 hours along the same path. So we need to set up a rational equation that determines the speed of the wind. Yeah, just assume the wind goes in the same direction. I know wind changes direction, but just assume that it goes, let's just assume it goes in one direction. Okay, so we're going to create a little box thing. Okay, so distance equals rate times time. So this is, I guess this will be against the wind, and this will be with the wind, right? So our units, we know we're going miles, so miles would be our distance. Hours here is going to be our time, and we know our rate is going to be miles per hour. Okay, so airplane travels 1,200 miles against the wind and 1,200 miles with the wind. Now the time it takes is going to be 4.5 hours, okay, along the same path. So what we need to do is we have to also know our average speed of this airplane. So our average speed is going to be 534. So I'm like, should I draw an airplane? I'm gonna try, right? Don't tease me. That's my airplane. Okay, anyway, so this is the wind. I guess this will be the wind. We can call it, you know what, we'll call it W. We'll call it W for wind. Okay, and this plane is traveling 534 miles per hour, right? So if you're going against the wind, you have to subtract how much the wind is holding you back. Now if you're traveling with the wind, this is going to go the other way, right? So if you had to go back in the other direction, this is 534 plus W. Now our time is going to be 1,200 divided by 534 minus W. The other one is going to be 1200 divided by 534 plus W. Now, what we can do is we can set up an equation. So this is 1200 divided by 534 minus W plus 1200 divided by 534 plus W, and that equals 4.5 hours. And that is essentially what we could use to solve for the speed of the wind. Alright. That was kind of long. Alright. Hopefully these videos will help. I'm going to make a part 3. Okay? See you.